Okay, welcome back, guys, to the week seven's discussion hours. And so, basically, in the last class, which was yesterday, we looked at uh, higher dimension in conduction heat transfer, which is basically trying to understand how do we solve heat conduction equations in the case when we had a steady state scenario, but now the temperature field was a function of two coordinates, which was x and y, and we typically solved a problem where we had a slab of finite length and width, and it was said that the upper face what was fixed at a temperature which is varying as a times x, where a was just a constant and x was the coordinate uh, specifically. And so you can interpret this as a given temperature profile which is linearly varying with the x direction, and this was imposed on the top face, as you can see. And given this, we were asked to derive an expression for a steady state temperature distribution, which in principle now will be a function of both x and y, because of the fact that now heat transfer has two possibilities. So heat transfer can take place in the x direction. It can also take place in the y direction as well, because of the finite width of the plate, which was b, basically. Okay. And given this scenario, we solved the heat diffusion equation, which basically was nothing but a Laplacian equation subjected to certain boundary conditions. And we used a technique which is known as the method of separation of variable. And then we basically look into the solution procedure. I eventually came out to be an eigenvalue problem, and then we evaluated the temperature profile, which at the end came out to be, yes, came out to be something like this. So it was a series solution where we need to sum it up to certain modes. So these discrete values of n, for instance, n equal to 1, 2, 3, up to, it can go up to infinity. So these discrete values of n, these are actually known as modes. This I forgot to mention it in the last class. So these values of n, which we, maybe I'll write here. So the discrete values of n, these are actually known as modes. Okay. For instance, like n equal to 1, n equal to 2, and this goes up to infinity. And these are actually called the individual modes of the problem. Okay. Now you might ask me that since this is a summation series involving certain discrete values for n, then how then at what n do we truncate this series? Okay, this is just a second. Okay, so the question is that since this is a series involving values of n, then at what n do we truncate this series? Okay, so the answer lies in the fact that uh, in how much computational power, let's say, you have. This is one aspect that you can say that, let's say you can compute up to n equal to 10, then you can go up to, let's say, 10, or you can go up to n equal to 20, that's so on so on. That's also fine, but you must try to understand that higher the value of n, the less powerful the mode is. So precisely it is n equal to 1 that is the most powerful mode, and this typically drives the solution. Okay, so you cannot like discard n equal to 1 and then start from n equal to 10 up to 20. Then your solution will not be mimicked, basically. Okay, so you cannot discard n equal to 1, but as and when you're increasing the value of n, the modes become less powerful, and then depending upon how much computational power do you have at your end, you can truncate the value of n up to that point. Typically you can continue up to n equal to 5 to 6, and this should give you a fair enough good result for the temperature profile. Okay, that's one aspect. The second thing is that the method of separation of variable, as we saw, uh, so the idea was that our three faces were at a temperature which was 0, and the upper phase was prescribed by a non-zero value of the temperature profile. Okay, so you can still apply the method of separation of variable. Let's say you have some fixed temperature, let's say T equal to 5 degrees Celsius on the three phases, something like this, which means that now the boundary conditions are not homogeneous in principle, but still you can apply the method of separation of variable, because you can always make a, a change of variable. For instance, let theta, which is equal to T minus, let's say T, so this is, so for instance we call it as T naught. Then you can always define a theta which is equal to T minus T naught. So then theta basically on the bound, on these three boundaries will always be equal to 0. Then theta will be 0 and theta will be 0 here. So even if you had a non-zero temperature which was the same in the three phases, you can still make a change of variable, and then you can, so you basically need to solve for this equation, which is del square theta is equal to 0. That's what you need to solve for, and just apply the method of separation of variable, and the rest the rest, everything else remains the same, the procedure and all the subsequent steps. But this is just a trick that if you encounter a scenario where there are prescribed temperature which is non-zero on the three phases, you can still make this kind of change of variable, uh, and make the boundary and make the other three boundary conditions homogeneous. Okay, so so this is the second aspect that I want to share in with respect to the exercises that we did yesterday. And with that, let's get started for today's discussion. And today we will look into another important aspect of heat of heat transfer involving conduction, which is known as the transient heat conduction. And in principle, we'll be looking into the lumped capacitance model, uh, and the reason, and we will see in details why this is called as the lumped capacitance model. Although in this week, this was the main agenda for discussion in the lecture series. So I believe you have a fair enough idea of of the the lumped capacitance model and the transient heat transfer analysis in detail. And then we will, if there is time, we will look into another important aspect which is known as semi-infinite solid. That is, how do we analyze heat transfer in case of semi-infinite bodies. But this is something that we will see if we have time, or else we'll do it in the next subsequent discussions. Okay, so so we'll begin by this understanding of the lumped capacitance model and in principle the transient heat conduction. So now, as the name suggests, you can infer that when I say something which is transient, this means that the temperature, since typically we are looking into heat transfer, so our prime variable unknown, or whatever you say, the prime variable of interest is the temperature, and this time our temperature is a function of time, and that's the reason why we bring into the word transient, which means that now we are looking into the unsteady solutions. So our assumptions which we had been using till the last class, that is, we are assuming steady state will not hold good. So we are now looking into the transient scenario of the problem. Okay, which means that your temperature in principle will be a function of time, and it can also in general be a function of space, and that's the reason why I will also write it as x bar vector. But if you are assuming your body to be a lumped body, it means that your temperature profile will just be a function of time only, and it will not be a function of space. Okay, for instance, let's say I consider a body. Okay, and you can understand an example, a typical example where in industry or in reality this kind of situation arises is when, so there is a process which is known as quenching. For instance, so in material science, what people do is they in order to study the behavior of materials, they first take the temperature of the body to a very high temperature, let's say to some initial temperature, let's say Ti, okay, which is much higher than the temperature of the surrounding, and then they drop this body into a surrounding pool of liquid. For instance, they drop this particular body into let's say water, which is at temperature T infinity, which is much less than the initial temperature of the body. And what they try to see is like how the temperature of the body varies in principle with time, but it so happens in such kind of bodies is that, so typically what will happen, so your temperature of the body which was initially at Ti, this will now vary within the body as variation in space, and it will also vary with time, because Ti was much greater than T infinity, so your temperature will, it will just try to equilibrate. So your temperature Ti will basically try to come down, and it will reach some equilibrium temperature, let's say T. Okay, so in this course your temperature will of course vary with time. Okay, and in principle it it should also vary with space. Okay, but if you're assuming your body to be a lump body, then what you are saying is that you are basically discarding this variation of temperature with space. So you are discarding this. Okay, which means all you are saying is that at any given time t, I repeat, which means you are trying to say is that at any given time t, my temperature at each and every position inside the body is spatially uniform. That is, it is not a function of the coordinates, or it's not a function of the points in the body where we are looking the temperature. Which means that, so I'll write it down, that you're assuming that your temperature distribution is spatially uniform. Which means that all you are interested now is to see how your temperature profile of the body vary in space. Okay, and such kind of bodies are known as lumped bodies, and that's the reason why uh, this analysis is sometimes known as lump capacitance analysis. We'll call it as capacitance. The reason why we call it as capacitance, I'll explain to you in the subsequent time. But at least now you know that why this is known as a lumped body. The reason why this is called as a lumped body is because we are assuming that at each and every time stamp, my temperature profile is spatially uniform. That is, it is not a function of space. So I'll write it down that at each time stamp, when the body cools, or it can be heated as well. So the other way is also possible. The temperature profile is spatially uniform. So my T is just a function of time, which is the small t here. Okay, and when these two cases are satisfied, we call the body as basically a lump body, and the heat transfer analysis that we will do by writing the heat diffusion equation and so on and so forth is known as the lump capacitance analysis. Okay, so that's the first thing that you need to understand when you speak about the word lump body or a lump capacitance analysis. The reason why we call it as capacitance, uh, we will see very shortly. Okay, so you know to this end, we will now discuss the lump capacitance model. Okay, and please pay attention, because this will help you to solve certain problems directly that is given in the assignment, I mean this discussion. So you can take some ideas into how basically uh, how to solve the problems in the assignment, so from this discussion. Okay, so let's again then consider the body that I was you know speaking about. So it's a lump body, as I said, having a thermal conductivity, let's say K, and the surrounding fluid, let's say, on which it is immersed, uh, maybe I will draw it like this. Okay, so this is the surrounding fluid on into which the lump body is immersed. Let's say this is at some temperature T infinity, and it possesses a heat transfer coefficient H. Okay, so what happens is, let's say at T equal to 0, at time T equal to 0, the temperature of this body, that is the temperature of this lump body, you can say that this is at T. So my temperature at T equal to 0 is some Ti, and you can assume that this is much greater than T infinity. Okay, kind of the quenching problem that I said. So what they do is, like as I said, they take the temperature of the body to some extremely high temperature, and then in heat treatment processes they quenched it into a oil bath or a water bath, or uh, things like that, where the surrounding temperature is much low. So in that case your temperature quickly drops, and this enhances the material property. That's the reason why this process is carried out. And what people are interested to see is how the temperature actually varies with time, disregarding the variations of temperature in space. And that's the reason why this analysis, as I said, is known as the lumped capacitance analysis. Okay, so as I said, at time T equal to 0, you are taking the temperature of the body to an extremely high temperature, let's say Ti, which we will call it as the initial temperature. And what you are interested to see it is, as at time T equal 0 plus, that is when time progresses, you are interested to know what is the temperature profile of the body. Okay, and in this context, as we have already carried out in the lecture series, if you consider a control volume, okay, if you consider a control volume uh, of this form, which encompasses the body as we commonly do, and if you are assuming that there is no heat generation taking place within the body, then you can simply do a energy balance, and then you can just say that what your energy that is going out, that is your E dot out, or your heat that is going out, that is equal to the rate at which the energy is changing inside the control volume. So that just becomes d dt of ECV. And if you just simplify this, and just solve it, because your energy is, because E dot out is just minus of H times the surface area of the body times the local, I mean, the instantaneous temperature, which is a function of T minus T infinity. This is the convection flux. And this becomes, rho CV. C is the heat capacity times dt by dt. So all you are writing is that what you are basically doing here is you are just writing E dot CV, ECV as mCV dt, which is the mass of the body. It is just mCT, and then m you are writing at rho times the volume times the specific heat times the temperature, which is a function of T. Okay, that's what you are doing, and from this you basically end up getting this form of the ODE. Okay, and then if you just simply, so this is an ODE in which you can apply the method of separation of variables, and if you do that, what you get is you basically end up getting an expression of of the temperature profile, which is like T minus T infinity by Ti minus T infinity is equal to exponent of minus T by Tc. Okay, it's just the intermediate steps that I'm skipping because you have already done this in the lecture series. But this is what you get when you are assuming that there is no heat generation taking place inside the body. Okay, and then you are only interested in seeing how your temperature basically varies with time, and then this is the expression for the temperature profile that you get. Okay, so this was the expression for the temperature profile for a lump body. Okay, where this Tc is known as the time constant, as we have already witnessed, and this has got an expression of rho times the volume, maybe I call it as, yeah, so it's rho times the volume times C by H times the surface area of the body AS, and this is known as the time constant. And sometimes in shorthand notation, people also write this as theta by theta I, which is equal to exponent of minus T by Tc, where your theta is defined as T minus T infinity. So your theta I in principle then this becomes Ti minus T infinity. Okay. So this is also another form in which the temperature profile of a lumped body can also be written. But the important thing you need to realize that this form is only applicable, okay, when there is no heat generation. Okay. There is no heat generation. Because in principle, if there is heat generation, then I hope you understand that then there will be one more term here, which will be like something like E gen, and then you will have another term over here, let's say Q dot times, basically what this is. So it is Q dot times like the volume, okay, and then you cannot, apply the method of separation of variable there, because it will now be an OD, it will now basically be a different form of the ODE. So you will not end up getting this form, this expression, if there is heat generation. And we will look into a problem at the end of today's discussion, that what happens if there is heat generation in case of a lump body. Okay, but rest assured that if there is no heat generation, you can use this form of the temperature profile into solving, either the time required, or finding out the temporal change in the temperature. So there are two things that you can calculate, because Tc is a property, and this is already known, because you can see that your time constant is a function of the density, its volume, the heat capacity, heat transfer coefficient, and the surface area. So it's kind of a property. So in this lump model, there are only two things that you need to calculate. Either you need to calculate the time, given that you are given a temperature at that particular time, or you are required to calculate the temperature when you know the particular time at which you kind of uh, want to get the temperature value. Okay, so these are the two things that you basically calculate from this lump capacitance analysis. Okay, now some important things that I want to discuss here is that, so in the definition of Tc, you have seen that Tc is equal to rho Vc by H times As. So this ratio of the volume of the body to its surface area through which heat is being dissipated. So remember, this V is basically the volume of the lumped body, and this As is the surface area through which heat is dissipated. And the ratio of this volume to surface area, this is known as LC, which is known as the characteristic length of the body. Okay, so this is known as the characteristic length of the body. Okay, for instance, like if you have a cube, and the 6 faces of the cube is responsible for dissipating heat, let's say to its ambient, then your LC will be the volume of the cube, which is A cube, by your surface area responsible for heat transfer, which is the 6 faces, because I'm saying that the 6 faces are equally responsible for dissipating heat to the ambient, and then your LC just become A by 6. So the characteristic line becomes A by 6. But for the same cube, let's say you are looking into the scenario where let's say now you are looking into a scenario where you are kind of insulating this face. Let's say you are insulating the bottom face, so the bottom face is insulated, so the only way heat can pass through is by the other 5 faces, and then your LC will basically be your volume a cube divided by 5a square. That is typically because you are kind of insulating the bottom face in this in this scenario. Okay, if the bottom face is insulated. For instance, if there is a sphere and it is dissipating heat to its ambient, then your LC will become again the volume of the sphere, which is 4 by 3 pi r cube, where r is the radius, by the surface area, which is 4 pi r square. Okay, and then your LC will just become to be equal to r by 3. Okay, so this is your characteristic length for the sphere. So remember, the surface area is that area which is responsible for heat transfer, okay, through which heat can be dissipated to the ambient. Okay, I hope this is clear. So in that case, you can then write your expression for the temperature profile, which we just wrote as T minus T infinity by Ti minus T infinity, and this is equal to, and we saw it as like exponent of minus T by Tc, where now you can write your Tc as rho times the characteristic length times the heat capacity by H. Okay, so we have written the time constant in terms of the characteristic length now. And we all know how to calculate the characteristic length from this exercise that we just now did. Okay, I hope things are clear so far. And I believe you are able to understand what we had been discussing. Okay, all right. So now we will be looking into one more interesting aspect of this lump capacitance model is then when, so as I had been saying that my temperature is spatially uniform, it is just a function of time. So naturally the question comes that when is this valid? Okay, so now we'll be looking into the validity of the lumped capacitance model. Yes, and as I said, the reason why we call it as a capacitance model is because you see there is something that initially storing the energy and then it is releasing with time. So we are involving a time constant into the picture here, and that's a similar behavior that in electrical analysis capacitors show, and that's the reason why this model is sometimes also known as a lumped capacitance model. Okay, that's the word capacitance come into the picture. Okay. Anyways, so in order to understand the validity of the lumped capacitance model, we'll again consider our whole, our lumped body as we had been doing. Okay. And let's say now I specify that in this lumped body, okay, the temperature at the center of this body is, let's say, at TSI. For instance, if it's a sphere, then TS, let's say, I'll call it as TS1. For instance, if it's a sphere, then TS1 is the temperature at R equal to 0, basically at the center of the sphere. And on the surface, we will call the temperature as TS2, while at the ambient, which is the fluid, the temperature is T infinity and with a heat transfer coefficient H. And the thermal conductivity, will call it as K. The surface area, will call it as AS. So in order to understand the validity of the lumped capacitance model, we are considering two temperatures at two different positions within the body. And we will later prove that these two temperatures are, very much equal to one another with respect to this T infinity if we are considering a lump model, and this is something that we will prove. But in order to do the proof, what we are saying is that let us now consider a temperature at the center of the body to be TS1, and and at the surface to be TS2. Okay, so then basically what this will happen is, like, if you now drop the body which was at some initial temperature Ti into a pool of fluid, let's say which has an ambient temperature T infinity with a heat transfer coefficient H infinity, then eventually the body will equilibrate. And like, if you want to understand it in a better way, if you plot the temperature profile of the body with respect to time, it will be at an initial temperature Ty, there will be a slow, there will be a transience where your temperature will drop, and then it will reach a steady state. It has to be, okay, because there will be, so it will try to equilibrate with respect to its surrounding. And let's say, so you understand that. So this is the transient phase, okay, where your temperature is actually varying with time. And beyond this transient phase is the steady state. Okay. So what we are now trying to do is, in order to understand the validity of the lump capacitance model, we are trying to figure out what happens in steady state first. Okay. So at steady state, and we are kind of disregarding this initial transience that is happening, and we are just looking into the steady state here. Okay. So at steady state, you can say that the heat that is going out of the body by conduction, this has to be equal to your q dot convection, and that is the typical energy balance or the continuity of fluxes we apply at the interface. This is just the continuity of fluxes at the interface. Okay. Interface meaning that we are just saying that whatever the heat that is coming out, that is coming from conduction, which is q and d, and this is going out to the ambient fluid by convection. That's all that we are writing, but this is only true because we are applying this at steady state. But we can then write this q conduction as the resistance. From the resistance model, this is delta t, which now becomes ts1 minus ts2, because this is what driving this. So this temperature difference between ts1 and ts2 is basically driving the conduction flux. Okay, so this then becomes ts1 minus ts2 divided by the resistance, which is L by K, and I will kind of write it as LC, which is the characteristic length, divided by K times AS. So all I am writing this is that it is just delta T by RTH. That's what I am writing for this Q dot conduction. Again, because there is no heat generation taking place into the picture here. And similarly, from the Newton's law of cooling, as we had been doing repeatedly, I can write Q convection as H times AS times Ts2 minus T infinity. That's all that I had been doing here. Okay, just writing the value of the individual heat transfers. Okay, so then what I can do is I can do some rearrangement, and I can write ts1 minus ts2 divided by ts2 minus T infinity as LC by KAS by H by what? Okay, I can write this as 1 by H times AS. Okay, I'm just doing nothing. I'm just picking it over there, and I'm just dumping this here. And then I'm just writing this term as 1 upon H times AS. That's what I've been doing here in the denominator. Okay, then you can see that this ts1 minus ts2, which is actually the difference between the between the temperature at the center point to the temperature on the interface, divided by the temperature difference between the interface and the ambient fluid. This is equal to LC by KAS, and this is 1 by H times AS. And if you pay a closer look, this is nothing but the resistance due to conduction to the resistance due to convection. Okay, and if you just simplify this then becomes ts1 minus ts2 by ts2 minus T infinity, and this is equal to HLC by K, and then this becomes RTH, which is nothing but the resistance due to conduction to the resistance due to convection. Okay, so so what you are essentially doing is that you are saying that the difference between the temperature at the at the center of the body to the temperature on its surface, divided by the temperature on its surface to the temperature of the ambient fluid, is equal to the resistance due to conduction by the resistance due to convection, and this is equal to HLC by K. Okay, now the lumped capacitance model is valid when these ratios, that is either this ratio or this ratio or this ratio, these three ratios has to be less than 1. Okay, and this is the scenario, and this is the scenario where the lumped model works. Okay, and in order to quantify this number that you have written here, this HLC by K, this has got a special name. This is known as the bio number. And for the lumped capacitance model to be valid, you can thus infer that your bio number, which we generally call it as Bi, this has to be less than 1. Okay, now if you pay a closer look at these ratios, you can say that the bio number is less than 1. You can also equally infer that your conduction resistance is less than your convection resistance, because this ratio is less than 1. You can also infer that this Ts1 minus Ts2, this has to be less than Ts2 minus T infinity. So physically, what does this mean? It means that at each and every time step, the difference between the temperature at the center of the body to the temperature on its surface, this is so less with respect to the temperature on its surface and with respect to its ambient. So you can say that at each and every time step, for the lumped capacitance model to be valid, you must have temperature within the body which is facially uniform, because you have already proved that your lump model is valid in the case when the difference between the temperature at the center of the body and the temperature on its interface, this should be sufficiently less than with respect to the temperature on the interface and with respect to the basically the ambient. And for this to be true, the only way it is possible that your temperature just needs to be a function of time, because you are all essentially into the zone where your bio number is less than 1. And that's the reason why we say that the body is spatially uniform. Okay, so this is the argument behind saying that, so this is the whole argument behind saying why your body is spatially uniform, that it has the sole meaning that the temperature difference within the body is very much less, or in other words, the conduction resistance is very much less than the convection resistance. Okay, now this is still an ambiguity, right? Because if you are using the lumped capacitance model in order to solve a problem, you still need a pinpointed value, that how much less is my bio number. So in order to solve problems, if oops so in order to solve problems, if your bio number is less than 0.1, you can rest assured that your lumped capacitance framework is valid. Okay, so for all cases where your bio number is less than 0.1, you can use the lumped capacitance model. Okay, all right, so this is the discussion behind trying to understand the validity of the lumped capacitance model, and the reason behind when we say that the temperature of the body is spatially uniform, that is, it is not a function of the position uh, at which we are trying to look within the body, at which we are trying to look the temperature. Or in other words, in simple language, your temperature is just a function of time. Your temperature within the body is just a function of time, and it is not a function of space. Okay, all right, I hope things are clear up to this point. Okay, so I want to discuss one more aspect into the form of the temperature profile that we just wrote. Is that, so what we saw is that in case of this lumped body where there is no heat generation, your temperature profile look like T minus T infinity by Ti minus T infinity, and this is equal to exponent of minus T by Tc, where your Tc, which we call it as the time constant, it was rho times C times LC by H. So if you just substitute the value for TC, we can infer some interesting things here. And this is what we will do. I'm just substituting the value for TC, and then this just becomes H T times H by rho C LC. Okay. Uh, Okay. And then what we'll do is we'll do some manipulation here. We will multiply the numerator and denominator, by LC. So this becomes HLCT by rho C LC square. And also what we will do is we will multiply the numerator and denominator by K, and then this becomes HLC K by K rho C LC squared. Okay. And then what we'll do is we will segregate certain things. So what we'll do is we'll just write HLC by K, and then the other things we'll write it as K times rho C. Okay, there is a T as well. Okay, so it is just becomes KT times rho C LC squared. Okay, and then you can infer that this is nothing but our bio number. Okay, so then this becomes exponent of minus bio number times this thing. I will write it as T by rho C LC square by K. Okay, where now we have a parameter which is known as the thermal diffusivity, and it is denoted by alpha. So this alpha is known as thermal diffusivity, and it is just the ratio of the thermal conductivity by rho times C. And it just says, so physically thermal diffusivity just says that how fast is diffusion with respect to the energy storage within the body, and that's typically the physical significance of thermal diffusivity. So then in principle this rho C by K, this just becomes 1 by alpha, and then I can write this form as exponent of minus bio number times T by LC square by alpha, where now you can infer that this bio number, this is of course a non-dimensional number. This is non-dimensional. Okay, therefore, so this bio number is basically non-dimensional. Therefore, this ratio of T by LC square by alpha, this also has to be non-dimensional. Okay, this also has to be non-dimensional, which means that this T by LC squared by alpha, okay, this is a non-dimensional number, and we call this as the Fourier number, denoted by FO. And this Fourier number is in principle representing two time scales. First the inherent time scale, and then this is another time scale that we have encountered, this LC squared by alpha, and this is known as the diffusion time scale. Okay, so in principle then we can write this temperature profile as T minus T infinity by Ti minus T infinity as exponent of minus bio number times the Fourier number. We generally call it as FO, where this Fourier number is equal to T by LC squared by alpha, where this Fourier number is now denoting two time scale. First, the inherent time scale, so it's the ratio of the inherent time scale to the diffusion time scale. Okay, so in principle, uh, this is also one of the forms of the temperature profile that you can infer for a lumped body without heat generation. Okay, all right. So this is another form of the temperature profile, where you can write your T minus, where you can write the temperature profile as an exponent of two non-dimensional numbers, bio number and the Fourier number, where this Fourier number denotes the ratios of two time scales of the body. Okay, I hope this is clear, and with this you can answer a lot of problems. This will help you to answer a lot of problems in the assignment of this week, that is week 7, and I hope you have understood this. Oops, sorry. Just a second. Yeah. Yeah. So I hope you have understood whatever we have discussed until this point. Okay, so this was all about, the background information or a little bit of glimpse of how this, lump capacitance model works. And why do we call it? So basically, first of all, you need to understand that why this is known as a lumped body. Second thing is that what do we mean physically when we say that my temperature profile is spatially uniform. This is the second thing. And the third thing is that why this is known as a capacitance. Why basically this is known as a capacitance model. And lastly, the fact that it's actually you can write the temperature profile as a function of two non-dimensional number that we just now saw, which is nothing but the bio number times the Fourier number. Bio number is essentially a property of the body because it is HLC. Actually, it's a property of the body and the ambient fluid, which is basically property dependent, and the Fourier number dictates two time scale, the inherent time scale of the body, that is the time scale actually which the body takes basically to to equilibrate its temperature with the ambient with respect to the diffusion time scale of this uh, of this body. So you can also infer that your lump model is valid for low bio number. As I just said, your bio number has to be less than 1, and in principle it has to be less than 0.1. You can also infer that your inherent time scale has to be much larger than the diffusion time scale of the body, uh, because you are saying that your temperature within the body is spatially uniform, which means that diffusion is so fast with respect to the actual temperature that the body actually takes to reach to the equilibrium temperature at steady state, which means that your lump capacitance model is valid for low bio number, it is valid for high Fourier number, because your inherent time scale is much higher than the diffusion time scale, because diffusion happens so fast. And that's the reason why your entire body is at the same temperature, which is basically T of T basically. Okay, and it is not a function of space. That is typically because the diffusion time scale is much faster, and that's the reason why your temperature kind of becomes spatially uniform. And then you are only interested in knowing the inherent time scale of the body basically. So this is another way of saying when the lump capacitance model is valid. It is valid for low bio number, and it is valid actually for high Fourier number, because again, because of the fact that your diffusion time scale is much uh, low. It's very much, so it's actually very much lower than the inherent time scale of the body. Okay, all right, lot of information that we have learned. I hope you understood this. If not, please let me know using the discussion forum of the group, and I'll be happy to address the queries. But now let's then look into a problem involving this lumped capacitance model, uh, and let's try to solve this. So what this problem says is that steel balls, so it's saying is that there are steel balls of 12 in diameter. So the diameter is given, is annealed by heating to 1050 Kelvin, and then slowly cool to 400 Kelvin. Okay, so in an air environment at which T infinity is 325 Kelvin. So what they have given is that your Ti, which is the initial temperature of the body up to which it has been heated, is equal to 1150 Kelvin. Okay, T, that is the equilibrium temperature, this is equal to 400 Kelvin. Okay, and T infinity, which is the environment temperature, is equal to 325 Kelvin. Okay, and all other properties are given. For instance, the heat transfer coefficient is given as 20. The thermal conductivity of the body of the balls are given as 40. Its density and heat capacity are given. So what they're asking is that estimate the time required for the cooling process. So indirectly, what they're asking is how much time does it require for the body to reach from this temperature to the equilibrium temperature 400 Kelvin. Okay, using the data that is given. All right. So first of all, it appears that you just have to use the values in the formula that we have just shared, but that is actually not the correct approach to solve this problem, because we still don't know that whether we can actually apply the lump capacitance model here or not. And for that, we need to check that is the bio number associated in the associated uh, with this problem that is actually less than 0.1 or not. Okay, so for that we need to check the bio number in order to apply the lump capacitance formula that we have just now saw. Okay, so in order to check the bio number, first of all you need to calculate the characteristic length LC, and for this case you know that your characteristic length is volume by the surface area, and for a sphere you know that your volume is 4 by 3 pi r cube by surface area is 4 pi r square. So your volume is basically equal to r by 3, or in terms of the diameter it just becomes d by 6, where you know that your d is 12 mm. So this is 12 into 10 to the power minus 3, okay, divided by 6. And indeed you can infer that so then how much is this? So this is 2 into 10 to the power minus 3. This is your characteristic length, okay, LC. So this means if you calculate the bio number from this, which is equal to H LC by K, okay, and then if you substitute the values, for instance, H is equal to 20 watt per meter Kelvin, LC is equal to 2 into 10 to the power minus 3, your thermal conductivity is 40. So if you calculate the bio number, this becomes 2, it is equal to 4 into 10 to the power minus 3, which is equal to 0.004, and this is, you know, did I do it? Okay, sorry, sorry for the calculation mistake. This is 2, and then these 2 and these 2 will cancel, so it is just 0.001. So your bio number is 0.001, which is, you know, less than 0.1. So since your bio number is less than 0.1, this means that the lump capacitance framework is valid. And since this is valid and there is no heat generation taking place within the body, then, you know, we can write the temperature profile as T minus T infinity by Ti minus T infinity, and this is equal to exponent of minus of the bio number times the Fourier number. Okay, and we know all the values. For instance, we know that my T, which is the equilibrium temperature of the body, it is 400. Okay, it's 400 minus T infinity, which is 325, by the initial temperature of the body, which is 1150 minus T infinity, which is 325. And then this is exponent of the bio number we have already calculated. This is equal to 0.001 times the Fourier number. So the Fourier number is T by, you know, LC square by alpha, LC square by alpha, where now you just need to calculate alpha here. So because your unknown is this T, right? You are required to find the time at which the body reaches 400 Kelvin. So your alpha, that we all know, it is just K by rho Cp, rho C, and your K was given to be 40, your rho is given to be equal to 7,800 times your heat capacity is 600. So if you do some simplification, your alpha will be around 4 by 700 times 15, and then you just need to, you know, substitute this alpha here, because LC is already known, that because your LC is 2 into 10 to the power minus 3. And if you just do this substitution and just solve for T, which I will not do because you at least you can do this in any standard calculator, so your T will roughly come out to be equal to 0.312 hours, or it will, or you know, it will come out to be equal to 1122 seconds. Okay, that's the time. So 0.3 hours, or around 1100 seconds, is the time your body will take to come from an initial temperature of 1150 to an equilibrium temperature of 400 when your ambient is at a 325 Kelvin temperature. With, in addition to all these properties, for instance, the heat transfer coefficient, the thermal conductivity, the density, and the specification. So that's the time it will require for the cooling process. Okay. Again, I repeat, in order to use this formula for the lump capacitance model, you first and foremost, the prime step that you need to do is to check the bio number, and you need to ensure that the bio number is indeed less than 0.1. Okay, because otherwise then this model doesn't work, because if your bio number is not less than 0.1, this means that you cannot disregard the spatial variations, or you cannot disregard the fact that your temperature is spatially uniform, and then you need to consider spatial variations into the picture. And this is something that we will see in semi-infinite bodies, where actually the variation in temperature with respect to space and with respect to time comes into the picture. Okay, but here, since the bio number is less than 0.1, we are assured, we can be sure that my temperature is just a function of time, and it is not a function of spatial positions within the body. And that's the reason why we can apply this form of the temperature profile that we have calculated for a lumped body. Okay, all right, I hope this is clear. And if this is clear, we will now solve an important problem associated with this lung body. But in this problem, you can, sorry. But what I was trying to say is that in this problem, you can understand the effect of heat generation in lump body, and then you figure out that we cannot directly apply the form of theta by theta equal to exponent of minus bio times the Fourier number, because there is heat generation taking place, and we need to start from the first principle. Okay, but before this, I would like you to actually go through this problem once. Okay, and read this problem on your own, and then try to understand how do you basically proceed for this problem, and then of course I will help you to find a solution possibly. So I've displayed the problem on your screen. I will just be back in a couple of seconds. Till then, you can have a look at the problem and try to think about how will you basically solve this. All right, let's get started with this problem. So first of all, let's try to read this, and let's try to figure out what do we need to do here. So it says that a chip that is of length L equal to 5 mm on a side and thickness T equal to 1 mm. So this length is basically 5 mm, okay, and this thickness, this is equal to 1 mm, is encased in a ceramic substrate. So basically the sides of this chip, it is being immersed in a, or encased in a ceramic substrate, and its exposed surface, which is the surface here, is convectively cooled by a dielectric liquid for which H is equal to, for which the heat transfer coefficient is given and its ambient temperature is given. Now what it says is that in the off mode, the chip is in thermal equilibrium with the coolant, okay, which is obvious. And then when the chip is energized, however, its temperature increases until a new steady state is established. This is obvious because you can think of it like the chips that are present in your laptop or in workstation, that whenever your laptop is turned off, then the chip which is embedded, which is present in your laptop, this is in thermal equilibrium with its ambient, which is air. Now whenever you are turning on your laptop, basically there is heat generation taking place within the chip, due to which its temperature would eventually rise to a new temperature which is greater than the ambient temperature. Now what you need to do is you need to cool your chips in the motherboard that is present in your laptop, and that's the reason why your laptop devices are provided with fans. And sometimes if you are doing this for a workstation which is very heavy, liquid cooling is also done, in order to cool or maintain the temperature of the chip to a to a temperature which does not exceed its design requirement, okay. And that's what they are saying. So when the chip is energized, however, its temperature increases until a new steady state is established. For the purpose of analysis, the energized chip is characterized by an uniform volumetric heat generation of this much magnitude. Assuming an infinite contact resistance between the chip and the substrate and negligible conduction resistance within the chip, determine the steady state temperature TF. Following activation of the chip, how long does it take to come within 1 degrees Celsius of this temperature? And the properties of the chips are given. So that's the problem that we need to find. So it's the problem that had been stated. For instance, there's a chip in your laptop. When you are switching off, when the laptop is in off mode, the chip is in thermal equilibrium with the ambient, which means Ti is just equal to T infinity. But when you are turning on the laptop, there is heat generation taking place, and because of which, in order to keep the temperature to below its design requirement, you are cooling basically the chip by using a liquid which is known as liquid cooling typically. And then you just need to find that what is the steady state temperature that your chip has arise because of this phenomenon. And also the transient case where that how much time does it take to basically reach to 1 degrees of this steady state temperature, okay. Now first of all, two things that you need to understand from this problem is that in this problem the temperature of the chip arises, or sorry, the temperature of the chip rises because there is a uniform volumetric heat generation of a constant magnitude of 9 into 10 to the power 6 watt per meter cube, which means that even though this problem has said that this is a lumped body, there is heat generation taking place in the chip, which means you cannot use the expression of theta by theta I equal to exponent of minus bio times Fourier in this scenario. Rather, you need to start from the first principle. And the second thing is that in the first part of the problem, they are asking you to just determine the steady state temperature of the chip, which is TF. So in principle, what actually is happening is will be more clear if we just draw the plot of the chip temperature versus time. So what is happening, initially it was at some Ti which is equal to T infinity. Then you are switching on your laptop, which means that this temperature is rising, okay. This variation we actually don't know, and we will be seeing that how this variation is with function of time, but we don't know. But at least we know that after an initial transient phase, oops. So what I'm saying is that at least we know that after an initial transient phase, your temperature will reach a steady state value, and we are calling this steady state value as TF. So in the first part of this problem, this is the steady state case, and this is the transient case. So in the first part of this problem, they are asking you that at steady state, what is the value of this TF? Okay, that's what they're asking. And in the second case, they are asking that how much time does it take to actually reach to a temperature which is just, which, the variation of which is just, 1 degree Celsius with respect to the steady state value. So they are basically asking you to calculate this particular time. That's what they're asking. So they're asking the value of this time, to be precise. Okay, that's the second case that they are trying to, uh, that they are actually asking us. Okay, so let's first do it. Let's first do the analysis for steady state. So first of all, to evaluate the steady state temperature, so so then what happens in steady state? First of all, you need to understand this in order to evaluate the steady state temperature. So at steady state, at this state, okay, in this scenario, so we know that if we apply, so if we are just, so what we'll do is we'll just choose a control volume which will just encompass, the chip, as we had been doing. We'll choose this control volume, and at steady state I can just say that, my energy, so if I just use the energy balance principle, okay, if I just use the energy balance at steady state, I can just say that whatever the energy that is being generated, okay, and whatever the energy that is being going out from the top surface of the chip, this has to be equal to 0. This is 0 because I am repeatedly saying that we are doing this as we are, applying this energy balance principle at steady state. Okay, so then my E dot gen is just the heat generation times its volume, which is just L square times the thickness T. We will not write the thickness with T because T will denote the time, so we'll call this as W. So the thickness, we'll call it as W, and the length, we'll call it as L only. So this is just L and W. So then my volume is L square times W. So this is the volumetric heat generation times the volume that I am writing. Okay. And this will be equal to E dot out, but E dot out we already know, right? It is H times the surface area responsible for heat transfer, which is L square, because the chip is only dissipating heat through this surface only, because the other surfaces are encased inside the ceramic. Okay, and that's the reason why your AS is L square, and then this becomes the final temperature minus T infinity. This becomes TF because we are trying to just calculate only the steady state temperature, which will now which actually is the temperature that the chip attains after this initial, transients. I hope this is clear. Okay, so that's it. We just require to calculate this TF. So your TF is just T infinity plus Q dot. So this L square and L square will get cancelled. So it is just Q dot W by H. And if you just substitute the values, your T infinity was 20. This was 9 into 10 to the power 6 times W was 10 to the power minus 3 meters by 150 is the height. Sorry, the heat transfer coefficient. Okay. And if you do this calculation, you will see that your TF comes out to be equal to 80 degrees Celsius. That's it. That's the steady state temperature of the chip, which means that the final temperature of the chip is 80 degrees Celsius. And this temperature is the final temperature, as I say, because we have calculated this by applying energy balance for the steady state scenario. Okay. So this answers the first, part of the problem, which is, I would say, the easier part. But remember, time and again, I am saying that this energy balance is applied for the steady state, and that's why we are not, writing the dECV by dt term, which is the rate of change of energy inside the control volume here, because this is 0 at steady state. Okay. I hope you understand that. I'll write it down here again. Since dECV, that is the rate of change of energy inside the control volume, is 0 at steady state. Okay, I hope this is clear. Now, in order to understand the second part, we need to look into this transient, this transient analysis. Because in the second part, what they're asking is that how much time does it take to reach to a temperature which is within 1 degree Celsius of this steady state temperature. Meaning that they're asking us to calculate that how much time how much time will it require to reach 79 degrees Celsius, which is just 1 degree Celsius apart from the steady state temperature. So basically they are asking this time t, okay, which at which the temperature is 1 degree within the steady state temperature, which is just 79 degrees Celsius. So what they are asking is you need to calculate this t when my temperature is 79 degrees Celsius, which means that I have to just calculate this particular time. Okay, and for this, since we are in the transient zone, we need to do the transient analysis. But remember, although this is a lump body, the reason why I'm just calling it as a lump body is because they have said that there is negligible conduction resistance. So anyway, we will assume this. We'll assume the chip to be a lumped body. Okay, but as I highlight, but there is a uniform volumetric heat generation. So this means that you cannot apply directly the formula theta by theta I or t minus t infinity by ti minus t infinity equal to exponent of minus bio times the Fourier number in this scenario. Okay, and for this we will start from the first principle, that is applying energy balance in the transient zone. Okay, and if we do this, this becomes obvious that minus E dot out, that is the energy that is going out, plus the energy that is generated, that is E dot gen. But now instead of it being 0, since we are looking into the transient zone, this will be just ddt of, so the rate of change of energy inside the control volume. This is what the energy balance looked like if we are applying this in the transient scenario. Okay. All right. Then now just let's write the values. So this E dot out is H times the surface area. I'll just write the surface area as L square because we already know it. And then this is T minus T infinity. Okay. Plus E dot gen is Q dot times L squared times W. And then we all know this. This is rho V, the volume, times C times dt dt. Okay. This is what the ODE we get, by applying the energy balance in the transient state. See, try to understand that without this heat generation, this term is 0, and then you will simply end up getting just this and this term. And if you just by applying the separation of variable, you can get that form of theta by theta as exponent of minus t by tc, or exponent of minus bio times Fourier. But since there is this energy generation or a source term present, you cannot directly get that, and we will derive the temperature profile in this scenario. But first of all, let's do some simplification. So I can write this volume as LC squared W, and then I can cancel this LC squared from all sides, and then I can just write this as minus H times T minus T infinity plus Q dot W. This is equal to rho C times dt dt. Okay. All right. Then how do we solve this? So ultimately what we need to do is we need to find an expression which governs T of T, and then we'll substitute this value of temperature as 79 degrees Celsius, and then we'll try to calculate what is the value of T. That's it. So for this we need to know the profile for this T basically, and then this is what we'll do. So let's write this term as something like this. This becomes H times this plus Q dot W, and this is equal to rho C times dt by dt. Okay, and what I'll do is I'll divide the entire expression by rho c, and then this becomes dt by dt. I'll take the terms to the other side. So this becomes h by rho c times the temperature, and then this becomes minus 1 upon rho c h t infinity plus q dot w, and this is equal to 0. Okay, and maybe I'll take the source term to the other side only. I'll keep the source term to the other side only. So this becomes this plus h by rho c t is equal to 1 by rho c times h t infinity plus q dot w. Okay, so what you can do is, since these are just constants, see the value of rho c and all these things are known, you can just call this, you can basically substitute the value and evaluate this. So I'll call this as a constant, let's say a, and since this is also known, h by rho c, I'll call this as, let's say, b. So in principle, we will now have to solve an ODE which is linear first order and of the form dt dt plus b times t is equal to a. So that's what you need to solve for. Okay, this is what you basically need to do, and this is easy because we have encountered this. So this is a non-homogeneous, first order ODE, and we know how to solve this because there is, so basically what we need to do is, like, we need to find an integrating factor, okay, which is equal to e power times integral b dt. Okay, so this is the integrating factor, and then if you calculate this integrating factor for this problem will just come out to be equal to b times t. So the solution, we know that it is, so the solution in this scenario will just becomes t times the integrating factor, which is b bt, that is equal to integral of, a times the integrating factor, which is b times t times dt. That's it. That's the solution. Okay, and if you just substitute the values for a and b, it will just be t, which is a function of time, times e power b is what? B is h by rho c, so it just becomes h t by rho c, and then this is integral a is equal to, but see, a is not a function, of, so a is not a function of time, so a will come outside the integral, and this will just be, so this will be just a times integral e power h t by rho c dt. You just have to do this integral. Okay, and you basically can write this t of t as just this a. So a is what? It is just 1 upon rho c times h t infinity plus q dot w. Okay, this is a, and then this integral. So this integral you need to do, if you do this integral, so e power, this integral will just be, e power, I think there will also be, anyway, so this integral will just be e power ht by rho c by, so this will be what? This will be h by rho c, so this will be, rho c by h, just the integration that I'm doing. You can just check the algebra from your end, and then in the denominator we also have this e power ht by rho c. Okay, I think that's it. Did I do any mistake? I'm just checking the algebra out. Okay, anyways, I'll just check the algebra. So maybe I'll just check the algebra, but anyways, you can now, so basically you just need to do this integration. I'll just check the algebra from my end, and I'll just post the result. But anyways, you just need to do this integration to, basically evaluate this t of t. And once you do this, you just need to substitute the value of, this temperature is 79 degrees Celsius, and you will eventually get the time here. But in principle, this is what, your this is what, your OD would look like in the presence of heat generation, because now we have a term which, says that there is this heat generation taking place within the body. Okay, please check the algebra once again. I might be wrong. I might have done some mistake in the algebra. But anyways, I will check that from my end once again. And I'll post the final results. But this is what in principle you need to do if there is a heat generation that is there in the body. And I repeat, you cannot directly apply the form of the temperature profile that we derive for a lump body, that is theta by theta equal to exponent of minus T by Tc, typically because we have this heat generation source term here. Okay. I think this is fine, but please check the algebra. I might be doing some mistake in the algebra. I'll check this in from my end and I'll post the final expression of t as a function of t, basically. Okay. But yeah, so this is what you need to do when you are dealing with such kind of problems, when there is heat generations, taking place in lump bodies. Okay. All right. So maybe we'll stop here today, because we have done a couple of good problems on lump body. So let's do a quick recap of what we did. So basically, we started off by trying to understand why do we call it as a lump capacitance model, and under what circumstances is this model valid. And then we said that this is true when your bio number is less than 1. And then we say that in principle it should be less than 0.1. And then we say that this can also be equivalently written as a terms of this bio number times the Fourier number. And then we saw that this Fourier number is essentially the ratio of two time scale, which is the inherent time scale and the diffusion time scale. And we equally argued that when that as the lump capacitance model is laid, it is valid for the case when bio number is less than 1. It is equally valid when your Fourier number is actually very much greater than 1, because your diffusion time scale has to be very much small. And this essentially explains why the temperature does not vary spatially in case of a lump body, because you have a very fast diffusion time scale in the problem with respect to the inherent time scale of the problem. Okay. And then we looked into a problem, basically a simple problem where we had applied this lump capacitance model, and then another problem which I feel is a good problem, where you are applying the lump capacitance concept, but in this case we have a heat generation. And this I feel is a very practical problem, because this typically happens in your laptop devices, because initially the chips in your motherboard are at room temperature. You turn on the laptop, you provide the cooling such that you want to maintain a steady state temperature, this TF. And you want to maintain this because you don't want this TF to rise higher, because then there will be a failure of the devices. And that's the thermal design requirement you want to keep. You want your temperature not to exceed that design requirement, as I was saying. So for that, you are basically cooling this chip either by liquid or by air, whatever you do. In this case, there is liquid cooling, I guess, because it's saying that it is cooled by a dielectric liquid. But anyways, in conventional laptops, instead of liquid cooling, generally there is air cooling. But in workstations where you require heavy computation, in addition to air cooling, there is also sometimes liquid cooling as well. And you prefer the liquid to be dielectric, typically because you don't want to uh, basically conduct heat and electricity. But anyways, in that context, this problem is very much relevant in practical sense. And so what we did is we calculated two things. First of all, the steady state temperature, where we say that at steady state, and just by applying an energy balance, whatever the energy that is generated, this will just be dissipated out. But in transient mode, where we are asked to calculate the time at which the final temperature is just 1 degree Celsius of the steady state value. In that context, we need to do the transient analysis, where now we actually solved an ODE, which is a non-homogeneous first order ODE. And then we use the concept of integrating factor to basically calculate that. I have to check the algebra once again, just to be sure that I am doing that right. But you can also do this at your end, and then please let me know what you get the final answer in this scenario. Okay. All right. Then this is what we did. So I didn't touch one concept, which is known as the semi-infinite solid, which is another case of a transient body. But here, as I said, in case of a semi-infinite body, you cannot neglect the spatial variations within the body. And actually this is true for bio number very much less greater than 1. That's the other end of the spectrum. So we will, in the next class, we will look into one or two problems associated with semi-infinite bodies, and then we'll move into solutions of heat conduction equations, how how do we basically solve that using numerical approach, and that's it. And after that, we will move into the radiation aspect of the course. So that's the plan for the next subsequent lectures. But till then, I hope you understood what we did today. I hope you liked it. And if there are any questions, please feel free to post it in the discussion forum, and I'll be happy to address them. And if there are any doubts, as I say, if there are any doubts in general, please post it in the discussion forum. And so we'll meet again in the next week at the same time using the same link from 3 to 5. Till then, thank you very much, guys. Please keep watching these videos. Thank you.